Because you know that as soon as you find out your system got a real parts which are positive, then you know that your system is stable. You expect to be stable and stable. Okay? Understand? Good. So, when you learn differential equations, you gotta learn how your solution related to your physical system. Okay, now you can see that these four functions, ET is the one really give us the real problem. The E minus T, cosine T, sine T, they don't give us any problem. So, let's look at this. For differential equations, we know that this is, that's the solutions we have. Initial condition with this, then we have the, given the initial conditions, then you can solve the coefficients. That's yt equal to e minus 2t minus e minus 3t. Okay. But this is assumed initially your system has non-zero initial conditions. If all your initial conditions are zero, then what happens? If my all initial conditions are zero, then what is that? What kind of homogeneous solution do you have? Huh? What does that mean? My initial condition is all zero. My building is initially all white, all zero. What happened? Nothing going on. Nothing going on means homogeneous solution is zero. Right? That means your transient response is zero. Right? So, all zero initial conditions that's important because very soon we'll see what happens. This is pero zero initial conditions that imply zero homogeneous solutions that imply zero transient response. So this is the physical meaning, zero transient response. That means before earthquake come in, my building is still. When earthquake come in, then it has to be vibrate. If the earthquake before earthquake come in, my building already shaking, that means I have transient response. But make the system even worse. Right? So that's a zero transient response. So in the dynamics, in the engineering system, we don't call homogeneous solution, we call transient response in the engineering systems. Mathematically, you call homogeneous solutions. Physically, you call transient response. Understand now? Okay. So, if you have initial conditions, then you have homogeneous solution, then you have transient response. Understand? Now, I'm talking about physics. Now, I assume that you know how to solve all this. So, but for this kind of transient response, we have the map we got there. the system decay about 4 seconds. In other words, even you have initial conditions for this case, then 4 seconds later, your transient response is gone. Okay, for example, if my building is, because of the typhoon, my building is vibrating, when typhoon is gone, in a few seconds, my building won't move anymore, for example, all right? The same thing when earthquake come in, now earthquake gone, then you have some transient response left. All right, I hope that earthquake is gone. That means my building will sooner or later decay, the vibration will decay quickly. So that's a transient response. That means we have zero force. That's just your system is moving because you have initial conditions, not because of your force. All right. So if you look at this case, you can see that your system decay in about 4 seconds. It's all gone. Your transient response. Now, for stable system, just like the example like this. Now, a stable system means transient response or decay right, like this in the vacuum. That's for stable system because all my real parts is -2, -3, and so because this real part is all negative, and this is for stable system. For stable system, that transient response will decay. I should say decay to 0. Will decay to 0 response. Most of the engineering systems like this building are stable system. Of course, this building is a stable system. If not, we won't have a class. All right. That's true. All right. Now, another subject. Non-homogeneous ODE. Assume we have the ET excite the system. I will tell you, non-homogeneous ODE, what does that mean in physics? In physical system. All right. So non-homogeneous solution means you have a forcing function like an ET. So this ET is your forcing function. Now how we solve it? Assume you know how to solve differential equations, so I won't do too much about this. But I want to explain to you what does that mean, non-homogeneous ODE. What does that mean, non-homogeneous solution? What does that mean in physics worlds? All right. Now, this is just some tricks how you solve the non-homogeneous solutions, homogeneous equations. This is tricks that if you ET, you write LET equal to L equal to DT D minus 1, and then if you write this way, then you can write in terms of homogeneous ODE to solve non-homogeneous ODE. It's kind of some tricks. So if you do that, then my general solution is this. So here I have my general solution is two terms. All right. You know. Now your homework. Let's go back to your homework. Your homework does have a forcing function. You know that, right? Huh? No? Oh, yes. Yeah, right. So when you solve it, you gotta be careful. All right? Now, if you solve this equation, we have two important terms. One is AET. Another one is plus C1E minus T plus C2T E minus T. Because we have repeated root here, so you have this. So C1E minus T plus C2T E minus T, that comes from the homogeneous solutions. Then AET, this comes from non-homogeneous solutions. Okay, now, we know C1, C2 can be solved from what? From the initial conditions. Now, how about A? What is A? I saw A. The easier way to sub this Y solution into the original differential equations. Then you can solve it. This is a way, this is one way to do it. You don't have to solve this way. But this is way so that it's, suppose you solve non-homogeneous solution ODE, but because I include